Imagine you're in a dark room, and someone throws a single pebble into a pond. You hear the splash, but you're not quite sure where it landed. So you start guessing. You say, maybe it hit here, or maybe there. Now imagine if the pebble could somehow land in all of those places at once until you turn on the light, and only then does it finally choose a single spot. That's a bit like how quantum mechanics treats particles like electrons or photons. They don't have definite positions or speeds until we try to observe them. Before that, they exist in a cloud of possibilities, known as a superposition. But the weirdness doesn't stop there. These particles don't just behave like tiny balls, they also act like waves. When you shine a beam of light through two narrow slits and onto a screen behind, instead of seeing two bright lines, you get a pattern of many stripes, an interference pattern. This happens even if you send one photon at a time. It's as if each photon splits and goes through both slits, interfering with itself. And only when you try to check which slit it went through does the pattern vanish. Just by observing, you change the outcome. The act of measurement itself affects reality. This strange rule isn't a bug, it's built into the fabric of how the universe works at the smallest scales. It's not that particles are playing tricks on us. It's that the classical way we think, objects having definite properties independent of whether we look at them, just doesn't apply in the quantum world. In that world, probabilities are not about our ignorance. They're fundamental. A particle isn't in a certain place and we just don't know where, it truly isn't in one specific place at all. And then there's entanglement. Imagine two particles born together in such a way that their fates are linked. You separate them by light years, and yet when you measure one, the other knows, instantly, as if distance doesn't matter. This spooky action at a distance, as Einstein called it, has been proven again and again in labs. It doesn't allow messages to travel faster than light, but it shows us that the universe is more deeply connected than our everyday experience suggests. It's like the particles are two parts of a single system, no matter how far apart they are. Quantum mechanics doesn't just describe odd lab experiments, it underlies the way stars burn, how atoms hold together, and even how your phone and computer work. Without it, there would be no transistors, no lasers, no GPS. It's not just a theory, it's one of the most accurate, powerful, and bewildering descriptions of nature we've ever discovered. To make sense of this strangeness, physicists use something called the wave function, a mathematical expression that captures all the possible states a quantum object can be in. It's not a picture of the object itself, but more like a map of potential outcomes. The wave function evolves smoothly and predictably over time, according to Schrödinger's equation. But the moment we measure something, say, the position of an electron, that elegant wave function suddenly collapses into a single outcome. This leap from possibility to reality remains one of the biggest mysteries in all of science. Why does measurement force a choice? What counts as a measurement? These are still open questions. Some interpretations try to answer them. One famous idea is the many worlds interpretation. It says that all outcomes do happen, but in separate, branching universes. In one world, the cat in Schrödinger's box is alive, in another, it's dead. Every quantum event splits the universe into versions where every possibility plays out. Wild as it sounds, this idea avoids the need for wave function collapse altogether. It says reality is just much, much bigger than we can see. Other approaches suggest that hidden variables might determine outcomes in a way we don't yet understand, or that consciousness itself could be tied to the act of measurement. But so far, no interpretation has been universally accepted. Quantum mechanics keeps working in experiment after experiment, no matter how bizarre it seems. In fact, it works too well, so precisely that we can measure effects like the electron's magnetic moment to over a dozen decimal places, and the theory still matches reality. And quantum theory isn't done surprising us. In recent years, scientists have been learning how to use quantum effects not just to describe nature, but to build new technologies. Quantum computers, for instance, promise to solve problems no classical machine ever could, by harnessing superposition and entanglement as resources. Instead of bits that are either 0 or 1, quantum bits, qubits, can be both at once, and linked in ways that allow for staggering parallel processing. It's like using the weirdness of the quantum world as a kind of superpower. This shift from observing quantum phenomena to engineering with them is one of the most exciting frontiers in science today. Quantum cryptography uses the rules of measurement to create perfectly secure communication, because any attempt to intercept a quantum message will disturb it, revealing the intrusion. Quantum sensors can detect incredibly subtle changes in gravity, time, or magnetic fields, opening up new ways to explore the Earth and the cosmos. Even biology might be more quantum than we once thought. Some researchers believe that processes like photosynthesis, bird navigation, and even smell might rely on quantum coherence, delicate states where particles remain in sync like dancers moving to the same rhythm. These states are usually destroyed quickly in warm, messy environments. But if life has found ways to protect them, it means evolution has tapped into quantum effects in ways we're only beginning to understand. The real challenge, though, is that our human intuition was shaped by a world of tables, trees, and tennis balls, objects that behave in a straightforward, classical way. But the quantum world doesn't play by those rules. There is no path, no trajectory, no solid object in the way we expect. Instead, there is potential, interference, fuzziness, and beneath it all, a reality that's still deeper, stranger, and more connected than our senses alone can grasp. And yet, we can grasp it, through mathematics, through experiment, through thinking carefully about what the universe is telling us. Quantum mechanics reminds us that reality isn't obliged to be intuitive. It's obliged to be consistent with what actually happens. And what happens, again and again, is something no one would have believed 100 years ago, until it was tested, confirmed, and used to build the modern world. In this way, quantum physics isn't just a set of rules for particles. It's a window into the soul of the universe, showing us that uncertainty is not ignorance, that observation shapes outcomes, and that the most fundamental truths may lie beyond the grasp of language, but not beyond the reach of the mind. The mind, in fact, is where quantum theory becomes not just a tool, but a mirror. When we ask questions about particles and measurements, we're also, in a subtle way, asking questions about ourselves, about what it means to observe, to know, to define reality. If observing a system changes its behavior, then the line between subject and object, observer and observed, is not as clear as we once thought. Quantum mechanics doesn't just describe the universe out there, it invites us to reconsider our role within it. This is part of why quantum theory has inspired not only physicists, but also philosophers, poets, and dreamers. It breaks open the neat categories we rely on, past and future, cause and effect, here and there, and replaces them with something fluid, probabilistic, and deeply interconnected. In the quantum world, opposites can coexist, time can seem to loop or stand still, and particles can influence one another across cosmic distances without a signal. It's a world that feels more like a thought than a machine. And yet, for all its poetry, quantum mechanics is, at the smallest scales, the so-called Planck length. Some physicists believe spacetime might be quantized, made of tiny, indivisible units like the pixels on a screen. Others suggest that space, time, and gravity might all emerge from more fundamental quantum entanglements, as if the geometry of reality is woven from invisible threads of connection. These are not just wild ideas, they are being tested in labs and telescopes today. And through it all, quantum theory remains both a mystery and a guide. A reminder that beneath the surfaces of things lies a deeper, shimmering order, one we can't quite see, but can feel in the mathematics, in the experiments, in the undeniable beauty of a universe that allows uncertainty, contradiction, and harmony to coexist. In this shimmering order, certainty becomes the exception, not the rule. What quantum mechanics teaches us, perhaps above all else, is humility. We cannot look at an electron and say with absolute confidence, it is here, and it is moving this way. Instead, we must speak in probabilities, in likelihoods, in waves of chance. And yet, from this uncertainty, the solidity of the world still arises, your hands typing on a keyboard, the atoms in your bones, the photons from distant stars entering your eyes. How does something so uncertain give rise to a world that feels so stable? Part of the answer lies in decoherence, the process by which quantum states interact with their environments and lose their fragile superpositions. When a quantum system touches the messy, macroscopic world, its many possibilities collapse into just one. It becomes classical. This is why we don't see coins existing in two places at once, or cats being both alive and dead. The quantum weirdness doesn't vanish, it just becomes hidden, drowned in the noise of countless interactions. But if we isolate quantum systems carefully enough, cool them down, shield them from vibrations, eliminate noise, we can preserve that weirdness and even use it. That's the heart of quantum engineering today, creating little islands of strangeness in a sea of predictability, and learning how to control them. Each success brings us closer to technologies that sound like science fiction, unbreakable encryption, ultra-fast computations, quantum internet, even new ways of modeling the brain or simulating entire universes. What began as a desperate attempt to understand the glow of heated metal or the structure of the atom has blossomed into a revolution that continues to unfold. The questions have become bigger, more abstract, but also more intimate. What is information? Can reality exist without observers? Is the universe fundamentally deterministic, or does it play dice, as Einstein once protested? No single experiment has yet answered these questions. But quantum mechanics gives us the framework to keep asking, keep refining, and keep wondering. It teaches us that not knowing is not a failure, it is a gateway. And within that gateway lies the infinite dance of particles, fields, and forces, each flickering with possibility, each echoing the same quiet truth: the universe is not a machine made of parts. It is a symphony made of chances. And in that symphony, we are not just passive listeners, we are part of the composition. Every time we measure, calculate, predict, or even dream, we engage with the quantum world. We make choices about what questions to ask, what systems to probe, what realities to collapse into being. This doesn't mean we control reality, but it suggests that reality and observation are more entangled than we imagined. Perhaps what we call the real world is less a fixed stage and more a dynamic unfolding, shaped by interaction, attention, and context. Even time itself, once considered a steady, absolute flow, begins to shimmer under quantum light. In some interpretations, time may not be fundamental at all, it could emerge from correlations between quantum systems, or be an illusion born from entanglement patterns. The past, present, and future may not be separate beads on a string, but aspects of a deeper quantum structure where cause and effect blur, and events are connected in non-classical ways. What we perceive as a linear timeline may be just one thread through an immense, multidimensional fabric. This is not just poetic speculation. Physicists are using quantum mechanics to tackle black holes, the Big Bang, and the boundaries of spacetime. Concepts like holography suggest that the information in a region of space may be encoded on its surface, just like a hologram. Other ideas propose that gravity itself could emerge from quantum entanglement, unifying general relativity and quantum theory in a single framework. These are bold, unfinished theories, but they reflect a growing sense that the universe, at its root, may not be built from stuff, but from relationships. Not from particles, but from information. Not from certainty, but from possibility. And yet, for all its abstraction, quantum mechanics remains deeply grounded in experiment. Every prediction, no matter how bizarre, has so far withstood the test of observation. Bell's theorem shattered the hope of hidden classical explanations. Quantum teleportation, once a thought experiment, is now demonstrated in labs. Superposition and entanglement are no longer mysteries, they are resources. What began as a philosophical challenge has become a toolbox for the future. The deeper we look, the more the quantum world reflects us back at ourselves. It shows us that knowledge is participation, that objectivity may have limits, and that understanding requires not just measurement, but imagination. Imagination, in the quantum realm, isn't a luxury, it's a necessity. Classical thinking can only carry us so far. To truly engage with quantum mechanics, we must stretch beyond the familiar, allow contradictions to coexist, and learn to think in terms of probability waves instead of solid objects, in terms of entanglement instead of isolation, in terms of becoming rather than simply being. This isn't easy, it takes courage to let go of certainty. But the reward is profound, a glimpse into the deepest architecture of reality. And perhaps that's the most striking thing of all. Quantum mechanics, for all its abstract formalism and complex equations, is ultimately a human story. It was built piece by piece through experiment, intuition, and the struggles of thinkers trying to make sense of a world that didn't fit their expectations. It challenged them, and now it challenges us, to see differently, to think differently, to be differently. It reminds us that truth may not be what we expect, and reality is often stranger, subtler, and more beautiful than anything we could have invented. In the end, quantum mechanics is not just a theory. It's a journey. A journey into the heart of matter and the edge of knowledge. A reminder that the smallest things, an electron's spin, a photon's path, can teach us the biggest lessons about the universe, and about ourselves. That in the quiet hum of probability and the flicker of possibility lies the echo of something timeless. Not certainty. Not simplicity, but wonder. Wonder, after all, is where science begins, and where it returns. Quantum mechanics doesn't give us all the answers. In fact, it often gives us better questions. It nudges us to ask not just what the universe is made of, but how we know it, why it behaves this way, and what it means to observe, to measure, to exist. It invites us into a world where the boundaries blur between observer and system, between knowledge and being, between mathematics and meaning. And this sense of wonder is not naive. It's rigorous. It's earned. Because for every unintuitive phenomenon, particles tunneling through barriers, objects being in two places at once, information seemingly traveling faster than light, there is a trail of meticulous experiments, peer-reviewed data, and equations that predict outcomes with uncanny precision. Quantum mechanics isn't magic. It's reality, just a deeper, more delicate version of it than we ever imagined. That reality is still expanding. As quantum computers move from the lab into the real world, as we entangle particles across continents, and as we probe the quantum structure of spacetime, we begin to see that this isn't a niche chapter of physics, it's the foundation of everything. From the birth of the cosmos to the flicker of thought in your brain, quantum processes are at work. Not as distant curiosities, but as the pulse of existence itself. And so, we keep exploring. We keep asking. We keep listening to the quiet music beneath the noise, to the faint interference patterns at the edge of knowing. Because in doing so, we're not just learning about electrons or photons, we're learning how to think beyond limits. How to stay open to surprise. How to find clarity inside paradox. Quantum mechanics doesn't promise comfort or certainty. But it offers something better, a universe that is alive with possibility, governed by laws more intricate and elegant than anything we could invent, and waiting, always waiting, for those brave enough to ask why. And in that question lies the essence of being human. To be human in a quantum universe is to live in the tension between what is known and what is unknowable. It's to look into the heart of an atom and find not a hard kernel of truth, but a swirling cloud of potential, a reality that only crystallizes when we dare to engage with it. It's to accept that uncertainty is not a flaw in our understanding, but a fundamental feature of the cosmos itself. And somehow, despite, or perhaps because of, that uncertainty, meaning emerges. This is what sets quantum mechanics apart from every other scientific theory before it. Newton's laws told us the world was like a grand clockwork, predictable and orderly. Einstein's relativity bent that clockwork into curved spacetime, beautiful and smooth. But quantum theory shattered the gears. It replaced certainty with probability, continuity with jumps, determinism with possibility. And yet, it did not replace order with chaos. It gave us a new kind of order, one that is probabilistic, contextual, and profoundly interdependent. This shift isn't just academic. It reshapes how we think about identity, about connection, about existence itself. In a quantum world, nothing exists in isolation. Every particle carries with it the memory of interactions past. Every system is part of a larger whole. The fabric of reality is not made of things, but of relationships. The universe is not a collection of parts, but a network of possibilities, each linked to the other in ways we are still learning to describe. And perhaps this is the most hopeful message quantum mechanics has to offer, that even in the smallest, coldest, most impersonal domains of physics, we find patterns of relationship, connection, and transformation. That at the very bottom of reality, the rules are not rigid commands but gentle suggestions, nudges that allow for choice, emergence, and change. In that sense, quantum theory is more than a branch of science. It is a philosophy, a lens, a way of seeing the world that honors complexity, embraces ambiguity, and finds beauty in the invisible dance of chance and structure. It tells us that light is both wave and particle, that matter is both here and there, that the world is both real and in some sense, unfinished, waiting for us to look, to ask, to wonder. And so we continue. Not because the answers are easy, but because the questions are worthy. Worthy not just of scientists in white coats, but of anyone who's ever stared up at the night sky and felt the vastness press gently against their chest. Quantum mechanics belongs to all of us, because it describes a universe that we are part of, not separate from. Its strangeness mirrors the strangeness we sometimes feel inside ourselves, the coexistence of contradictions, the unpredictability of choices, the mystery of consciousness, of thought, of time. It reminds us that complexity isn't chaos, and that uncertainty doesn't mean disorder. It means openness. It means possibility. Possibility is what allows a particle to tunnel through a wall. It's what lets the future remain unwritten. It's what gives rise to creativity, emergence, evolution, and thought. In a deterministic universe, everything would already be carved in stone, there would be no room for surprise. But the quantum universe is different. It leaves space for freedom, for emergence, for the unexpected to become real. We are born into that space. We move through it. We shape it, and it shapes us. This is perhaps the greatest gift quantum theory has given us, not just new tools or technologies, but a new relationship with knowledge itself. A recognition that we do not stand outside the universe like distant observers. We are entangled with it, entwined in its probabilities, participating in its unfolding. Each observation, each experiment, each act of attention is not merely passive, it's a collaboration between mind and matter, between question and answer, between what is and what might be. And that means something profound, that in every small act of curiosity, we echo the same forces that govern the stars. That the same laws which shape the birth of galaxies are at work when a photon bounces from your eye. That the universe isn't just out there, it's also here, within us, through us, becoming what it is by virtue of our being part of it. In that way, quantum mechanics doesn't just expand our understanding of the cosmos. It reconnects us with it. Not as something to conquer or control, but as something to listen to explore, to wonder at. It tells us that the universe is not a cold, mechanical grid, but a living field of possibility. And in the quiet spaces between equations, in the subtle flicker between yes and no, it whispers the most extraordinary truth. You are part of this mystery, too. You are part of this mystery, not by accident, but by nature. You, with your questions, your uncertainties, your ability to imagine and doubt and dream, are as quantum as the particles that dance unseen through your bones. The boundary between the observer and the observed, so sharp in classical thinking, dissolves here into a kind of cosmic intimacy. You influence what you study, and what you study shapes what you become. Awareness and reality are not opposites, they are partners in a subtle dialogue written in the language of probabilities and light. This doesn't mean that we invent reality. But it does mean that reality, at its deepest level, is not fully separate from us. In quantum mechanics, measurement is not just a passive snapshot, it is a creative act. The world, in its tiniest moments, is not fixed until it is touched. Until something, somewhere, asks. And so in that sense, each moment of perception is not just noticing what is, but helping decide what will be. This is a terrifying idea, perhaps, for those of us raised in a universe of objectivity, where things simply are. But it is also an empowering one. Because it means that existence is not just a finished painting we hang on the wall, it is a canvas still wet with color, still changing beneath our gaze. It's easy to feel small in a quantum world. After all, it operates on scales far below our senses. The units are femtometers and zeptoseconds, the energies invisible, the forces subtle. And yet, the quantum world is not separate from the one we inhabit. It is its foundation. The atoms in our hands obey these same rules. The thoughts in our minds are patterns of quantum interaction. The very light that lets you read this now is quantized, flickering, probabilistic. And so, to study quantum mechanics is not to step outside ourselves, it is to return to the roots of what we are. To explore the invisible architecture beneath the surface. To touch the delicate web that holds everything together and find, not coldness, but pattern. Not randomness, but meaning. We often think of science as stripping the world of mystery. But quantum mechanics does the opposite. It deepens the mystery. It tells us that the more we learn, the more there is to learn. That the universe is not made of answers, it's made of questions that grow richer the closer we look. And perhaps that's what makes it so human. So human, because we, too, are made of questions. From the moment we open our eyes to the world, we ask, what is this? Why does it move? Where do I end and the rest begins? Quantum mechanics doesn't flatten these questions with simple answers. It respects their complexity. It meets our wonder with its own. It tells us that the most fundamental layers of reality are not built from certainty, but from openness, from the infinite branching of what might be, from the shimmer of choices not yet made. And in that shimmer, we find ourselves reflected, not as isolated minds, but as nodes in a great web of connection. Your heartbeat, your memories, your breath, all arise from processes that are quantum at their core. There is no hard border between the physics of the stars and the physics of your thoughts. Both are made of the same strange fabric, shaped by the same laws. You are not standing outside the cosmos trying to understand it. You are the cosmos, learning to recognize itself. This is not philosophy dressed as science. It is what the math, the measurements, the experiments continue to show us, that nature is not built from brick and stone, but from resonance, interaction, and uncertainty. That to know something is not to pin it down forever, but to share a moment with it, to bring it into form through attention. And so, quantum mechanics is not just the story of particles. It's the story of meaning in a probabilistic world. It's about how structure arises from fluctuation, how patterns bloom from noise, how beauty persists even when the rules are strange. It teaches us that light can behave like a wave until we ask it to act like a particle. That matter can tunnel through walls, dance in two places at once, and change its very nature depending on the questions we pose. It shows us that asking how changes what is. And it whispers, again and again. You are not separate. You are not fixed. You are possibility, woven into the fabric of possibility. To live in a quantum universe is to live in a world where the future is not written, where the act of looking changes the landscape, where even the smallest things contain echoes of the whole. It is to be part of a vast, delicate unfolding, a universe not of things, but of becoming. A universe of becoming means that every moment is alive with potential. Nothing is fully settled, nothing entirely closed. Even in the vacuum, what we once thought of as nothingness, quantum fields tremble, flicker, give rise to spontaneous particles and their twin opposites, appearing and vanishing in a heartbeat. Emptiness, it turns out, is full. Stillness is alive. Silence hums with the probability of creation. And so we begin to see, the quantum world is not detached from the poetic. It is the poetic, made real through equations. It is uncertainty rendered measurable, mystery made testable. It allows the world to breathe, to surprise, to evolve, not through chaos, but through deeply structured ambiguity. Quantum mechanics doesn't say, anything can happen. It says, many things can, within limits, and how we engage with them matters. This is why the quantum revolution changed not only physics but the very language of possibility. It gave us tools to understand the unpredictability of radioactive decay, the chemistry of stars, the design of microchips. But it also gave us metaphors to explore consciousness, freedom, creativity, concepts that had long hovered just outside the reach of classical science. If the tiniest units of reality do not obey strict, deterministic rules, then perhaps free will, too, is more than illusion. Perhaps the self is not a machine but a pattern, fluid, emergent, irreducibly complex. And still, at the heart of all this, is humility. Quantum mechanics has taught us that nature does not yield its secrets easily. That what seems solid may dissolve upon inspection. That what we observe depends on how we ask. And that the universe will always remain just a little ahead of our grasp, beckoning us to follow deeper. Yet we do follow. With lasers cooled to near absolute zero. With entangled photons shot through fiber optic cables. With telescopes peering into quantum shadows cast across billions of light years. Each time we reach out, we learn a little more. Each time, we reshape our idea of what it means to know. And maybe that's the deepest truth of all, that knowledge isn't a destination, but a relationship. A dance between what is and what might be. Between us and the cosmos. Between the measurable and the mysterious. And in that dance, we are never merely observers. We are participants. We are questions. We are, in the most quantum sense of the word, alive. Alive, not just biologically, but fundamentally, as expressions of a universe that does not stand still, that does not obey rigid scripts, but instead unfolds like a symphony with infinite branching melodies. Each breath you take, each neuron that fires, each choice you make is entangled with a universe that has always held room for uncertainty, for emergence, for story. Quantum mechanics reminds us that the world is not carved in stone. It is written in wave functions, fluid, shifting, always in flux. Even time, which feels like the most rigid structure of all, may only be an emergent feature of deeper quantum rules. Some physicists believe that at the smallest scales, time disappears, replaced by entanglement and symmetry. The ticking of clocks, the march of past to future, these may be shadows cast by a more intricate, timeless structure. One in which cause and effect are less like links in a chain and more like harmonics in a vibrating field. This doesn't diminish our lives. It elevates them. Because in a quantum universe, meaning is not imposed from above. It is built from the bottom up, from relationships, from context, from interaction. There is no central conductor dictating the score. Instead, we are all co-composers in a universe where the music arises from the way we listen, the way we measure, the way we relate. We find this principle everywhere once we begin to see it, in the way ecosystems emerge from millions of interactions, in the way cultures evolve, in the way consciousness itself may arise from entangled activity across the brain. The quantum world tells us that complexity can grow from simplicity, that coherence can arise from chaos, that identity is always dynamic, defined not by isolation, but by relation. And so we return to that central paradox: the more precisely we understand the quantum world, the more it reveals the depth of our connection to everything. We are not outside looking in. We are inside, looking deeper. We are part of the probabilities, the entanglements, the waves of possibility. To know that, and to feel it, is not just science. It is awe. It is a moment of stillness inside the storm of becoming, a realization that beneath all uncertainty lies something more enduring, the sheer, staggering fact that we are, here, now, wondering. And that wonder, too, may be quantum. That wonder, flickering quietly behind every question we ask, may itself be the most quantum act of all, a superposition of curiosity and humility, of seeking and surrendering. It is the human wave function stretched between what we know and what we long to know, collapsing only when we dare to look closer. And in that glance, in that measurement of the unknown, we do more than reveal a particle's path, we reveal something about ourselves. We are, in essence, the universe becoming aware of its own laws. When we split an atom, entangle photons, or chart the orbits of electrons, it is not just an external manipulation of matter. It is the cosmos reflecting inward. Every quantum experiment, from the double slit to quantum teleportation, is a whisper from the universe to itself, a moment when reality takes measure of its own potential. Perhaps this is why the deeper we go into quantum theory, the more it begins to sound like a form of listening. The equations don't just describe, they respond. They don't tell us what is in some objective, frozen way. They tell us what can be, if we choose to look. Quantum mechanics doesn't provide a single, authoritative voice, it offers a chorus of possible realities, each humming with the potential to emerge into being. And though we cloak it in mathematics, this song of potential is also profoundly poetic. It reveals a universe that does not demand certainty from us, but participation. A universe that does not punish ambiguity, but thrives on it. One that does not rush toward a single destiny, but blossoms across a vast field of intertwined fates. In this way, the quantum world holds a quiet hope, that we are not bound by what has been, but opened by what might become. That the fabric of existence is not stitched with absolutes, but woven with choices. That even at the smallest, coldest, most indifferent scale, where particles blink in and out of being, and energy lives as probability, there is room for surprise. For emergence. For wonder. And so, If we are to take one thing from the quantum world into our everyday lives, let it be this. Nothing is entirely fixed. Every interaction matters. The future is not written. And even in the silence between particles, there is room for something new to appear. Because the universe is not finished. And neither are we. We are unfinished, and that is our gift. To be unfinished means to remain open, to learning, to becoming, to unfolding in directions we cannot yet imagine. Just like a quantum system, we exist in a state of ongoing possibility. Every thought we have, every choice we make, every word we speak collapses a bit of potential into reality. And then, the wave expands again. New branches. New futures. New chances to redefine ourselves, not just as observers of the cosmos, but as active threads in its grand entanglement. The most haunting beauty of quantum mechanics is that it offers no final answers. No tidy conclusions. It does not wrap the universe in neat laws that explain everything. Instead, it hands us the deepest of mysteries and says, "This is yours to explore." It reminds us that reality isn't a locked vault, it's an open question. And that even the most advanced equations are only approximations, whispers, fleeting outlines of something more vast than form. In this sense, quantum mechanics is not only a science, it is a practice. A way of approaching the unknown with precision and respect. A way of being in the world that acknowledges how little we truly control, and yet how deeply we matter. It is both a discipline and a reverence, a simultaneous embrace of rigor and wonder. And in the end, perhaps the most quantum truth of all is this. We are not separate from the story we seek to tell. We are the story, mid-sentence. We are the question, not the period. We are the echo of the Big Bang, still resonating. A flicker of awareness within the probability cloud of the universe. So keep asking. Keep wondering. Keep collapsing possibilities into meaning. Because every act of understanding, no matter how small, draws the infinite a little closer. And somewhere, between the uncertainty and the awe, between the math and the mystery, you may just catch a glimpse of the universe looking back. And when it does, when the universe looks back through your eyes, through your thoughts, through your quiet moments of wonder, you'll know, this was never just about particles or equations. It was about connection. About the fragile, astonishing fact that in a universe governed by chance and governed by law, you exist. You are aware. You are capable of asking questions that matter, of feeling beauty in the unseen, of finding meaning not in certainty, but in the shimmering, shifting dance of possibility. Quantum mechanics doesn't give us a map. It gives us a mirror. And in that mirror, we see not just the strange nature of reality, we see the reflection of our own potential. So let the mystery remain. Let the equations guide, but never silence, your awe. Because to understand the quantum world is not to solve it. It is to enter it. To live inside its questions. And to discover, again and again, that the deepest truths are not the ones we grasp, but the ones we grow into.